Welcome back to yet another video on the AK5706. I'm still Bobby Tufino, and I'm still an apps engineer here at AKM Semiconductor. The AK5706 is very good at identifying relevant audio so that you can keep your system SoC asleep as long as possible. Now we're going to dive right into this video without much of a recap, so if you haven't watched the video on noise tracking yet, please go ahead and do so now. Let's get started. We said earlier on that we don't even bother with any kind of acoustic analysis until we've identified a sound that is loud enough for us to want to learn more about it. When we encounter an audio event that fits our loudness criteria, we pass it on to the acoustic analysis block. As I mentioned in the previous video, the AAA performs analog time and frequency domain analysis on incoming audio. This analysis only costs a few microamps. We'd never have power numbers that low if we were running FFTs to figure out what kind of sound just occurred. Let's have a closer look at the acoustic analysis block. The acoustic analysis block consists of two bandpass filters as well as the frequency analyzer, the time analyzer, and the classifier. Let's start with the frequency analysis. Incoming audio comes in through the two bandpass filters, and the frequency analyzer looks at that incoming content. The frequency analyzer compares the energy present in the two bands. If the audio event contained more energy in the low band, it's considered to be a low frequency sound. If there's more energy in the high band, we call it a high frequency sound. Of course, high and low are relative, so you as the user can go into the AK5706 GUI and adjust settings, such as the bandpass filter cutoff frequencies, in order to determine what you consider to be a high frequency sound or a low frequency sound. The time analyzer's job is to determine if a sound is of long or short duration. In the GUI, we set a time analyzer detection window and a duration threshold. Let's say that we pick 100 milliseconds as the detection window length and 50% as the duration threshold. If the audio event spends more than 50% of that 100 milliseconds above the NLD's level threshold, we call it a sound of long duration. Below 50%, we'd consider it to be a short sound. At this point, we can begin to classify the incoming audio across 4 regions, based upon spectral content and duration. The acoustic activity analyzer can be programmed to reject audio that is classified into any of these regions, further allowing the user to refine what kind of audio events they would like to listen for. Here are a few examples of sounds that you'll be familiar with and how they'd be categorized more or less. This is not an exact science. A door knock is a very brief, deep thud sound, so it's going to fall into the category of low frequency with a short duration. You may think of human voices as being high, but actually most of the energy in the human voice is going to be in the low hundreds of hertz, so that'll tend to fall into the low frequency, long duration region. Breaking glass tends to be high frequency content and very brief. Okay, time for some more demos. Let's start with classification. First, I'll show you how well the AAA identifies sounds. When I shook my keys over the board, the LED turned on, meaning that we've identified a sound as relevant. In this case, I wasn't listening for anything specific, so it just means that the sound was louder than our noise level detector's threshold. I then go to the GUI, which tells me that the AAA has identified that as a high-frequency, short-duration sound as expected for shaking keys. I'll do the same for a door knock. This time, the AAA identified this sound as low-frequency, short-duration. And here's one more. Wake up. When I go back to the GUI, you can see that the AAA classified my voice as low frequency and long duration. A baby's voice is much higher than an adult's, and the sound of a crying baby can feel quite interminable, so that pretty clearly falls into the high frequency, long duration category. Let's say that we're building a baby monitor, and we don't care about chirping birds or door knocks or anything else. Remember, the AAA allows the user to reject audio from whichever regions they'd like. That's great. You can make sure not to classify as relevant any sound that's very different from what you're interested in. But unfortunately, a given type of sound doesn't usually fall perfectly into one of the AAA's quadrants. So if you just set the system up to reject most of those regions, you will successfully ignore sounds that you're not interested in, but you may also miss sounds that you care about but happen to fall just outside of those boundaries. Luckily, you can use the AK5706 GUI to adjust the boundaries of each quadrant. If you do that right, you can really zero in on the sounds of interest. Okay, maybe we're not that into baby voices after all. Maybe we're more interested in non-infant human voices. We just have to aim for the low frequency, long duration region and then adjust our criteria for high versus low frequency and long versus short duration to match our area of interest. I would go into the GUI and disable the regions that I don't care about, leaving just the low frequency, long duration region. Let's give it a shot. Wake up. Notice that the wake up LED only came on when I spoke. The system didn't wake up when I rattled my keys or knocked on the table, because we masked those types of sounds out. If programmed carefully, the AAA can do a very good job of keying in on sounds that you care about and weeding out uninteresting audio events. That means that your power-hungry SoC gets to stay asleep for longer, which makes your battery very happy. The AK5706 also has a human voice-specific parameter set. The AK5706's voice-specific mode can narrow the recognition region from this to this. The voice-specific mode is only meant to do that one thing, so it isn't as flexible as the 4 regions approach that we've been talking about, but you get a far smaller, more targeted classification region than you would just by tuning classification boundaries. Here's a quick demo. Wake up! We were playing some fairly loud pub noise near the microphone board, but the system didn't wake up despite the various noises and distant voices. It only woke up when I actually spoke. Our testing for accurate voice detection showed that moving from the 4 regions approach to the voice-specific parameter set reduced the incidence of false positives from 37% to 10.5%. That means that we can eliminate almost 90% of potential false positives, still for only 30 microamps. Regardless, we were able to correctly detect speech 100% of the time, even in 4 regions mode. One additional feature of the AK5706's Acoustic Activity Analyzer is that it can detect and distinguish between T3 and T4 alarms. For anyone who isn't aware, T3 is the beep pattern emitted by smoke alarms in the US, and T4 is the pattern for carbon monoxide alarms. We do some filtering to reduce reflections. These alarms are pretty loud, so that sound tends to bounce around a reverberant room pretty well. Since the patterns are standard and known to us ahead of time, we look at the length of the beep, the time between one beep and the next, and how many beeps there were. We need a full cycle of beeps to identify the pattern correctly. Similar to the last demo, we played some noisy room sounds and the system correctly recognized the alarm as a T3 pattern. That's it for our dissertation on the Acoustic Activity Analyzer. I know it was a lot of material to cover, and there's more to come. In the next video, we're going to talk about the second big system design challenge for voice-activated products, namely, how do you preserve audio that occurred while your SoC was still booting up? Thanks for hanging in there. Head over to akm.com for more cool stuff, and we'll see you next time.